So hey nerds, this is Suman, and in this video I'm going to show you the beautiful relation that obeys for photons. So in my last two videos I had derived the relation that the position and momentum uncertainty in terms of kinetic energy and in terms of relativistic energy. So in that particular video, the equation that we got, equation 1, or you can say the first video is the special case of the second video. So we got basically two different relations, and that is only for the massive particle is compared to photons. Just for like electrons and protons, the equation holds true. So because why, if you had looked up into that relation, you can actually see that there is a Compton wavelength and there is a rest mass term in that equation. In both of the case there is a rest mass term. So actually the rest mass is only valid for massive particles, but the photon is itself the massless particle. And you can actually derive another relation for photons, uh, showing the position momentum uncertainty in terms of photon. So photons do not actually carry mass, but they have certain definite momentum and energy. So basically we are going to derive the energy wavelength uncertainty based on photon, or you can simply say for photons. And I'm going to show you the medium dependence and independence relation also. So actually the uncertainty decreases as you increase the, if you change the medium. So if you're doing experiment in vacuum, and if you're doing the same experiment in another medium, your uncertainty goes on decreasing. So isn't that so beautiful thing about quantum mechanics? So, and if you take the uncertainty ratio, if you take the ratio of two uncertainties, for example, in medium and with respect to vacuum, you will end up getting the square of refractive index. Either it is reciprocal or it's just the square. I forgot that. I will later derive it and I will explain it. But the two ratios of two uncertainty actually depends on medium. So for different kind of medium, you would have different kind of uncertainties. And this equation, if the equation actually holds true, you can consequently say that the photon do not carry actually rest mass. So if the equation holds true, well, I don't know really whether the equation is true or wrong, but I'm going to apply it for photons. And let's see if some researcher is seeing this video. Please, you can do the experiment based on my result. So it's not my result, okay? Based on this idea, and you can check it out whether this math actually holds true or not. So basically I'm again saying that this is not my idea. I didn't invent anything. So it is the another way of actually looking the Heisenberg uncertainty principle. So Heisenberg just gave it as the energy position wavelength, sorry, position momentum uncertainty. So but I had taken a further step and took it momentum relation to the wavelength uncertainty relation. So and I had derived it for relativistic condition, kinetic energy based condition, and I am applying the same concept for the photons. And if the photons were in a different media, how the uncertainty goes and increasing and decreasing. So let us dive into the whiteboard. So nerds, let us go and derive the uncertainty relation for the photons. So I'm writing here my introduction, or just the thing, position wavelength, position wavelength uncertainty, position wavelength uncertainty for photons, position wavelength uncertainty for photons. And so basically I'm actually bored of doing the same experiment again and same derivation again and again and again. So I'm always starting from Heisenberg, Heisenberg uncertainty, from Heisenberg uncertainty principle. From Heisenberg uncertainty principle, I can write delta x into delta p is actually greater or equal h cut upon 2. So basically your h cut is nothing but h over 2 pi. This is known as reduced Planck's constant. So this would be my equation number first. Okay, and I know that from de Broglie hypothesis, from de Broglie hypothesis, from de Broglie hypothesis, the momentum can be written as h over lambda. So h is famous Planck's constant and lambda is the wavelength associated with the particle when it would be in motion. So P can be written as h upon 2 pi. I am just manipulating things to make it in terms of wave number. So momentum can be written as h cot. So it is nothing but reduced Planck's constant times k. So this would be my equation number second. Okay, so I'm using equation 2, using equation 2 in first. So what would I get? I will get delta x into delta. So in terms of momentum, I can actually write h cut k, and it is greater or equal to h cut by 2. So if the both h cut cancel out each other and vanishes, we would end up getting, we would get a delta x into delta k is greater or equal 1 over 2, right? So basically we can write uncertainty as, we can write uncertainty is delta k. I would like, in terms of delta k, I would write it dk over d lambda into delta lambda, where delta k is uncertainty in wave number and the corresponding there will be some uncertainty in wavelength. So what would I get? I will get delta k is d upon d lambda, and it is d. Okay, the wave number is nothing but 2 pi over lambda, and it is delta lambda. So I will get delta k is negative 2 pi over lambda square. So if you know how to take the derivative, if you're looking this video, you know how to take the derivatives, and it is delta lambda. And I would like to assure you that the sun will shine in a second. I know. I would like to assure you that the uncertainties are always positive, so I'm taking the magnitude. Right, so I will end up getting delta k. The uncertainty in wave number is 2 pi over lambda square delta lambda, and this would be my equation number third. So I am deriving it from the fundamental concept of Heisenberg uncertainty principle. So I am not deriving anything new, but I am showing, you can see the uncertainty principle in terms of various factors like the position, momentum uncertainty, position, wave number. It is already derived, and the textbook also shows this fact, but generally the textbook do not shows what I am showing. So I am not showing something new, and I don't really, professor, know about this fact or this concept or not, but this has to be added. So in terms of momentum you will end up getting this, and in terms of wavelength you will end up getting something very much interesting. So you can use using equation 3 in second. So this would be my equation second, this would be my equation number, I will, let's say it's equation number third, and this would automatically become my equation number fourth. So using equation 4 in equation 3. So what would I get? I will get delta x into 2 pi over lambda square, and the inequality sign delta lambda is greater or equal, that's inequality sign, and that is 1 over 2 pi. So you can actually express the change in moment, position, the uncertainty in position and wavelength can be written as greater or equal lambda square upon 4 pi. So the uncertainty in position and uncertainty in momentum, the product of uncertainty in position and the product of uncertainty in position and the wavelength is nothing but it is greater or equal lambda square upon 4 pi. So the uncertainty increases if you increase the wavelength of light, right? The product of uncertainty actually increases if you increase the wavelength of light. You can actually see from here that the uncertainty, the product of uncertainty is actually proportional to the lambda square. So if you put the relation, if you take delta x and delta lambda in y-axis, and if you put lambda in x-axis, you will end up getting a parabola. You will end up getting a parabola. So basically this is a negative sign actually doesn't make sense. You will end up getting this, something like this, because if you neglect that, if you don't neglect it, you will end up getting parabolic equation. So that's basically parabola. So we had replaced the uncertainty in terms of wavelength. So in terms of wavelength, I am getting delta lambda is uncertainty, and in terms of product of uncertainty, I am getting lambda square upon 4 pi. So I would like to replace it in terms of, let us say, momentum. So the what we have to do? So this would be my equation number fourth. This would be my equation number fifth. So from equation number fifth, we get delta x into delta lambda is greater or equal lambda square upon 4 pi. So I am taking p square over p square, and it actually makes sense to you also. So this would be delta x into delta lambda greater or equal. So lambda p is nothing but your h square. So again we have started the de Broglie wavelength. If you had looked up into the de Broglie wavelength, we will end up getting lambda p is, and if you square it, it would be h square upon 4 pi t square. So you can actually see from here that I had converted the same relation, equation 5th, into the equation 6th, but this equation 6th contains the momentum inverse. So I'm not saying, I would not have to say inverse, but the uncertainty, product of uncertainty decreases if your momentum increases. So basically equation 4 represents the same equation in terms of wavelength, and equation 6 represents the same equation in terms of momentum. Okay, so from relativity, I think it is from special relativity, from special relativity, the energy squared is nothing but rest mass energy squared plus p squared c squared. So for photons, the rest mass is 0. We are assuming that, and it is actually come from Einstein's equations. So E square is nothing but P squared C squared. So for P squared we get E squared over C squared. Right. So for P squared we can actually substitute here in terms of energy. So I'm going to use equation number 7. Right. So let me rub this. And actually using equation 7 in 6. So what would I get? Delta x into delta lambda is greater or equal h square upon 4 pi into, so the basically p square is nothing but e squared over c squared. It is actually the e squared over c squared. So this is the speed of light in vacuum. So delta x into delta lambda greater or equal h squared c squared over 4 pi e squared. So I don't want to write h squared. I want to write in terms of h cut. So in terms of reduced Planck's constant. So I am delta x into delta lambda is greater or equal to, let me show this. So I can write h square c square by, I'm writing here is 4 pi square e square, and I'm multiplying with pi. It actually makes sense. So I'm writing delta x into delta lambda is greater or equal h upon 2 pi whole square pi c squared over e squared. So delta x into delta lambda is actually greater or equal to, I can write h upon 2 pi is pi h cot square c squared over e squared. So you can actually see in terms of energy terms. So if we had noticed something very much interesting, that actually firstly we get position and wavelength uncertainty is directly proportional to wavelength. So again we will end up getting in terms of inverse of momentum square. So if and we are also getting in terms of inverse of energy square. This is a very beautiful thing. Look at this. It's actually square. It's actually square. So if I divide something from the same uncertainty, and let me show you this. So up to here, I think you right. I think you know something. This is equation number. Let us be equation number 8, right? And from here you can also see that the uncertainty actually decreases uncertainty actually decreases. If you plot the graph, delta x into delta lambda and the energy graph, you will end up getting something like this. The uncertainty goes on decreasing as the energy of photon increases. So the violet color have maximum uncertainty because the energy of violet is very much greater as compared to the energy of red. So the violet color photon actually shows greater uncertainty in space as compared to the red color photon in the same space. Yes, it is. I think it makes sense to you. You know that the energy is proportional to frequency from Planck's radiation law or the quantum nature of light. So energy of violet is greater than energy of red because the frequency of red is very much less as compared to the energy of violet. So if you know in terms of, so the uncertainty, let us say it is delta x delta lambda, uncertainty for violet is actually greater than, sorry, what I'm saying. So the uncertainty for red color, okay, did I missing something? I think the energy actually, if the energy increases, the uncertainty decreases. So the uncertainty, as the violet color has greater energy, its uncertainty is very much less as compared to uncertainty with red color photon. Right? Did it make sense? What do you think? The energy of violet is greater, so it have lesser uncertainty as compared to the energy of red is lesser, so the uncertainty increases. So you can actually say that within the same space, if you take the red colored photon and violet colored photon, you measure the uncertainty based on their relation energy term, you will end up getting the violet color has lesser uncertainty in space as compared to the red color photon in that same space. It is very much beautiful concept. I hope it makes sense to you guys. I hope it makes sense. I'm using suffix delta x delta lambda v for violet color and delta x delta lambda r for red color. So basically we found that the uncertainty is actually directly proportional to its wavelength square, inversely proportional to the momentum square, and actually inversely proportional to the energy square. So E is the energy of photon, right? Energy of photon. You can replace E in terms of frequency, h nu. H nu. As the frequency increases, the uncertainty again decreases. Yes, because the violet color has greater frequency as compared to the red light. So what I'm doing now, I got delta x into delta lambda is greater or equal pi h cot square c squared over e squared. So this is for vacuum. Let's say for vacuum V. For vacuum. For other medium, let's say for other medium. For another medium. For another medium, delta x into delta lambda is actually greater or equal to pi h cot square v squared over e squared. I think it doesn't make sense to you. Let me reconfirm this. So basically we know that the refractive index of medium is nothing but the speed of light in vacuum with respect to speed of light in that particular medium. So you can write C as mu v. So you can actually write delta x into delta lambda for any medium for vacuum is greater or equal to pi h squared t squared. So c squared you can write as mu squared v squared over e squared, right? Pi h squared t squared mu squared over v squared. So this is for vacuum. So delta x into delta lambda vacuum greater or equal to pi h squared t squared v squared over e squared into mu squared. And doesn't this equation looks very much familiar to you? This is in terms of speed of light in vacuum, and this is in terms of speed of light v in another medium. So I think I can actually write it as delta x into delta lambda for vacuum is greater or equal to delta x into delta lambda for any medium m times mu is squared. Any medium times mu is squared. So you can actually say that the uncertainty is maximum in vacuum is compared to the another medium m. Uncertainty actually decreases. So if you take the ratio of these two, if you divide both sides by delta x into delta lambda for vacuum divided by delta x into delta lambda for any medium m, it is always greater or equal to mu squared. It is always greater or equal mu squared, and this is the direct consequence of the uncertainties are positive because the refractive index is here positive in nature. So for air or vacuum you have mu is equal to 1 and these two terms are actually same. So for another medium the value of mu actually changes. So you can run an experiment in any medium m, and if you multiply it with the medium's squared refractive index, you will end up getting the same result if you done the experiment in vacuum. So let me re-clarify you that if you had done the same experiment, if you had done an experiment in medium, and you will get the product of uncertainty in momentum, uncertainty in position and uncertainty in wavelength in a medium m, and if you multiply the medium square, if you multiply its refractive index square, you will end up getting something very much interesting if you had done the same experiment in the vacuum. So you can actually say that the uncertainty is maximum in vacuum. So there is a lesser chance of locating particle in free space as compared to in the medium. The equation is telling us that. So basically I had show you in terms of energy relation, in terms of wavelength relation, in terms of momentum, in terms of this. And if you take the ratio of two uncertainty, if you had done an experiment in vacuum and if you had done experiment in another medium, and if you take that ratio, the ratio is always greater or equal to square of refractive index. So you can actually conclude this fact that the uncertainty in wavelength and momentum in vacuum by uncertainty in medium is greater or equal always constant. Either you would get the constant quantity or you will end up getting the greater than the mu squared term. So you can actually find the refractive index of different medium very precisely if you had done your experiment very precisely calculating the uncertainties. So you can actually find out the refractive index of medium if you had calculated already your uncertainty in vacuum and uncertainty in medium. So I hope this also makes sense. So for this much, I would like to say thank you for watching this, and if you had found any mistakes over here, you can actually comment down it below. And if you are a researcher who is actually looking this video, you can actually run an experiment in this phenomenon, whether it works or not. So guys, if you're watching this, just share this to the whole world and let us show the very much interesting concept about quantum mechanics using a simple algebra, not using the momentum operator, energy operator, position operator. So I think I hadn't made the quantum mechanics worse than what the scientists had done, because they use something very much new terms, the operators. So I had used the basic algebra, and it actually follows. I'm actually following the basic algebra. I hadn't used the complex math. So basically, I hope you guys really satisfied with this equation, and you can actually now visualize the energy moment, visualize the Heisenberg uncertainty principle in various terms. For photons, this equation actually holds true. For photons, this is the position wavelength uncertainty. And if you had already seen my two videos, that is for massive particle as compared to photons. They are protons, electrons, alpha particles, and whatever the if the particle has mass, they actually obey. And you can actually conclude that if the experimental result match with this equation, you can actually conclude that the photon has rest mass. Photon do not have rest mass energy. So this will be the direct consequence of finding that the photon has do not rest mass energy. So for that, bye bye.